In the first problem, I was testing you not only on the idea of a projection, as I hinted at in the problem description, but I'm also testing you in this case with problem solving. Okay, there are some ideas here that we didn't talk about. In particular, finding a vector perpendicular to W. How do you find a vector perpendicular to W? And also doing a reflection of a vector along a line instead of a projection. Okay, so I was expecting people would look things up. I was trying to give you a little bit of hints on things that you might need to look things up as far as what this means. You do want to draw a picture, and it's probably good to make it as accurate as you can. The vector W has components 1, 4. So it's going to look about like this. V is an arbitrary vector, x, y. One good thing to do with problem solving is to pick something particular for V, that is to try to get you warmed up, so to speak. I'm not going to do that, but I will draw, one possibility for V might look like this. But it's an arbitrary vector. It's got arbitrary components, x and y. W, when you put the base at the origin, is along some line through the origin. But there's also a line that's perpendicular to that. Going to look about like this. Not a super great drawing, but that's approximately a line perpendicular to W. Yeah, I didn't draw that very well. Pretend that's a right angle. I think it was because I moved over here and I was looking at it from this angle, and so it made it seem wrong. That made that seem right at first. Okay. Pretend that's perpendicular to W. That's the line we want to reflect V across. So you need to look up what reflection means. It means draw a perpendicular like that. That looks a little bit better for perpendicular. And then continue it the same distance on the other side. And so the reflection we're after, if V looks like this, is going to look about like this. And this does end up being a linear transformation, though I didn't say that. You do want to find a formula for it. You could call this T of V, and your goal is to find a formula for it in terms of x and y. I said you want to figure out a vector perpendicular to this line along W. One way to do that is to realize, okay, this line's got a slope of 4 along W. So this line, it seems reasonable, at least should have a slope of -1/4. You can look it up. Slopes of lines that are perpendicular to each other are called negative reciprocals of each other. If this has a slope of 4, this has a slope of -1/4. That's one bit of problem solving you can do. Another bit of problem solving you can do is that you can figure out one particular vector along here. If W has components 1, 4, should seem reasonable that one vector you could write down there would have components 4, -1. I'm going to go ahead and call that W subperpendicular. It's actually kind of a common notation. Having components 4, -1 would be one vector perpendicular to W. And the dot product of W with W perp here is 0. 1 times 4 is 4, plus -1 times 4 is -4. 4 plus -4 is 0. These two vectors are perpendicular. You're going to learn in a lecture, if you haven't watched it already, lecture 9B. Also, that's also called orthogonal, kind of a fancy name for perpendicular, but it's worthwhile having a new name for it, as we will see later. So that's an example of a vector that's perpendicular to W. One example, not the only example, any non-zero scalar multiple of this. Another bit of problem solving to do here is to think about vector addition and subtraction and the geometric meaning. Where is the projection vector? I'll give you a hint to use that along this line. Well, it's going to be the vector starting at the origin going out to here. It's the shadow of V along that line. If light rays were coming in perpendicular to that line, the shadow of V would be this green vector that I'm drawing here. That would be the projection vector of V along not W, but W perp. Maybe I'll just call that P for short. The question is, how can we get from V to its reflection, T of V? That's the final thing you got to realize before you try figuring out the final formula. How do you get from V to T of V? One way to get from V to T of V is to add this vector to V and then add it again. Or in other words, add 2 times that vector. What's that vector right there? You can relate it to P and V. V plus this vector is P, in fact, right? By the geometric meaning of vector addition. Watch it closely here again. Go along V to its head. Then add this vector by putting its tail at the head of V. Brings you down to here, but that's the same as P. V plus this vector is P. Therefore, that vector, what should I call it? Something else. I don't know. A. V plus A is P. Therefore, A is P minus V. I have to add these 2 vectors to get P. And if you add these purely symbolically, V plus P minus V, the V's will cancel, giving you P. And we know by the geometric meaning of vector addition that it does have to give you P. So it looks like symbolically, in terms of these symbols here, T of V should be V plus 2A, doesn't it? Yeah, V plus 2A. And now it's just a matter of simplifying this. I can replace A with P minus V. And then I can distribute the 2 through and get 2P. V minus 2V is going to be just minus V. So in terms of P and the original vector V, this is T of V. Now we're not done. We got to write it in terms of X and Y. We got to figure out P in terms of X and Y. Use the projection formula there. We're projecting V along W perp. The formula says that's V dot W perp over W perp dot itself times W perp. Okay, that's XY dotted with W perp is a particular vector here, 4, -1. That's got to get dotted by itself in the bottom. And then we need to simplify that. You might wonder, what if we used a different vector parallel to that line, like 8, -2 instead of 4, -1? The answer is this would simplify to the same thing. It doesn't matter what vector you pick along that line. The formula for the projection will simplify to the same thing in the end. You can try it for yourself to confirm it. Do those dot products. On the top, you get 4x minus y. On the bottom, you get 16 plus 1. 16 plus 1, 17. Looks like you get, let's see. Simplify this here. 4x over 17 times 4 would be 16x over 17. 16 17's x. And then we got a minus y over 17 times 4 would be minus 4 over 17y. Double check my work here. On the second component, 4/17 times -1 is -4/17 x. And then -1 or negative y over 17 times -1 is positive 1/17 y. That's P Now we can finish the problem. That goes in here. So we get 2 times this vector. And then don't forget to subtract the original vector v, which is xy. See if I can do this all in my head here. Let's see, the x in the first component is going to be 32/17 minus 17/17, right? 15/17 x. And then with the y term in the first component, it'll be 2 times -4/17 is -8/17, and there's no y there, so we get just a -8/17 y. And then down in the second component, -8/17 x, and there's no x over there. And then 2/17 y minus 17/17 y would be minus 15/17 y. That looks like the final answer. Where v here is xy. Something very important that I want to add to this is the following. This could also be thought of as a matrix times a vector. This is a linear transformation. To confirm that, how can we write this as a matrix times a vector? Listen very carefully. This is really important. We can separate this to a linear combination of vectors. I could first separate it as 15/17 x, -8/17 x, plus -8/17 y, -15/17 y. And then with this vector, I can factor out the scalar x, and this vector, I can factor out the scalar y. I can write this as a linear combination like this. A linear combination of vectors is a sum like this, where you have weights in front of the vectors. These scalars are sometimes called weights or coefficients. And this was something you should have known before exam 1. It was one of the multiple choice questions. What's the definition of a matrix times a vector? It's a linear combination of the columns of the matrix with the entries of the vectors as the weights. That's what this is. It's this matrix, 15/17, -8/17, -8/17, -15/17. There's some symmetry here. Times this vector, that column vector. We could write this as A times the vector. I called this vector V in this problem. In the lectures, I typically call it X vector. Make it bold-faced. Confirming this is a linear transformation. If you can write the transformation as a matrix times a vector, then it is linear transformation. Yes, it's linear in X and Y here as well, with no constant terms being added. That's another reason that it's a linear transformation. You don't want constant terms with linear transformations because you want them to satisfy these kinds of equations. And the reason they end up satisfying these kinds of equations that you see here, where u and v are vectors and alpha is a scalar, is because matrix multiplication times a vector also satisfies similar properties. However, when you write it with a t, with a linear transformation, t is a function. So you say t of u plus v equals t of u plus t of v. You say t of alpha times u is alpha times t of u. If I replace t with a matrix A, I could write formally similar properties, but it would be multiplication, not function. T is a function, A is a matrix. If I replace the t with the matrix A, I would say A times u plus v equals A times u plus A times v. And A times alpha times u is alpha times A times u. They're very much related. T of v does equal A times v, but technically speaking, it's a different concept. T is a function, A is a matrix. T of V is A times V. T is computed by matrix multiplication. Okay, subtle ideas, but they typically do cause some confusion sometimes. So you want to have those concepts clear in your mind. Yes, this matrix has some symmetry to it. Evidently, reflection matrices, you could call this a reflection matrix. That comes from reflecting across some line. Maybe it typically has some symmetry to it. Second problem is pretty important as well. By the way, projections are going to come up. We're introducing projections now. They're useful for physics, as you may know from your physics classes. Projection vectors are going to play a big role for us in the last 2-3 weeks of the course as well, though they're going to be generalized in some pretty challenging ways, but they're pretty important. They end up being important if you've heard about Fourier series. They end up being important for Fourier series and partial differential equations. Yes, projection vectors are useful for those things, but generalized, a bit more abstract.